You are watching part 2 of Unit 2 of Quick Precalculus Review for Calculus, Part 16. Unit 2 has a very long-winded name, but I think it all fits together nicely, and I think if you stay with me, you'll see that it's worthwhile to think about all these things together. Inverse functions, power functions, logarithmic functions, and alternative representations of exponential functions, including use of the special number e. These will all fit together in the context of compound interest problems. So we're going to bring out all these themes. Parts 1 through 14 looked at comparing and contrasting linear and exponential functions. We'll still think about linear and exponential functions in this context. In this particular video, we're going to be thinking about the compound interest formula. We used the compound interest formula in the last video. Here we're going to be more just thinking about it and making some graphs. We're thinking about it as defining the accumulated balance as a function of the principal and vice versa. In other words, you've got a bank account, you put some money in it, that's called the principal. It stays there a certain amount of time, you get a balance at the end, that's called the accumulated balance. If we think of the interest rate, the time, and the number of compounding periods per year as fixed numbers, then the accumulated balance is actually a pretty simple function of the principal. It's linear, and in fact more than linear, it's a proportionality. The graph actually goes through the origin. What does this vice versa mean? It means we can turn it around. We can think of the principal as being a function of the accumulated balance. That's the idea of an inverse function. And we're thinking about then inverse functions in the simplest kind of context here to start with. So let's go down here. Here's the compound interest formula as it stands. Again, T is the time in years. R is the interest rate as an annual rate. It's also called a nominal rate. N is the number of compounding periods per year. It is compound interest. P is the principal, the amount you deposit at the start, and A is the accumulated balance. P is also called the present value in some context, and A is also called the future value in some context. Here was the example we considered in the last video. We solved this example. It's got three parts to it. We're imagining we're back in the 80s and we have this great savings account with an 8% interest rate compounded quarterly. Part A, we use the compound interest formula to find out how much the initial deposit of $1,000 would grow to after 10 years. In Part B, we tried to figure out how much we should deposit right now for it to grow to $10,000 in 10 years. And finally, we also found something called the doubling time of the account, which happens when you have compound interest. And here are the solutions down here. You can see $1,000 for 10 years, 8% annual interest compounded 4 times a year for 10 years, ends up with a balance of $22.08 and 4 cents. With the second question, we wanted to have $10,000 in the account at the end of 10 years. P, the principal, what should we deposit right now? The answer was $4,528.90. And with the doubling time, we had to experiment. We had to experiment with the formula. What value of T would cause the principal to double? And we had to try different things for T based on the values of P, R, and N. And it doesn't matter what P was. The amount of time it takes to double was the same. And in this case, it was about 8 3/4 years. Alright, in this video the main focus is going to be on these equations right here. And I'm going to go ahead and use function notation. I'm assuming you've had precalculus. We're doing precalculus review, so function notation shouldn't be anything new to you. I'm going to give this function a name. That's all function notation here initially is. It's just a name. I give this function a name. I'm calling it f. Alright, f is the name of the function. F of p represents the output of the function when the input is p. P is called the input or the independent variable. A is the name for the output, the accumulated balance. That is the dependent variable. Again, f is just the name for the function. When I write this, it's implicit then that I'm thinking of the other letters, r, n, and t as fixed. And by the way, whether something is fixed or a variable is all in your head. It's all in how you're thinking about it. So I am free in my mind, and you are free in your mind, to think of letters in math as either representing constants, fixed numbers, or variables, things that can vary. It's all in your head, okay? That's an important thing to realize. Anyway, so we've got this function. Let's go ahead and enter these numbers except for the p. I'm going to go ahead and enter the r, the n, and the t back up here. Get rid of this other stuff. And then I'm going to define a function in Mathematica. This program, again, is Mathematica. If this is the first video you've watched, that might be new to you. I'm defining a function f in this way. This is the basic kind of syntax. So f is going to be the name of my function. Mathematica requires square brackets instead of parentheses around function arguments. And when you first define the function, you need to put an underscore after any variables, in this case, the p. The colon there is not absolutely necessary, but I like putting a colon there. And let's go ahead and type in that formula. Actually, I can essentially type it in with this to help me here. Put a p in front and get rid of this negative exponent. That is the function f of p. Again, r, n, and t are fixed, and now I can evaluate this function at any value of p that I want. For example, when p is 1,000, that will be the answer to the first question back up here, 2208 and 4 cents. I plug in p equals 1,000. I confirm that answer for part A. Maybe I should put it up here just to have it in the right spot. Maybe I should put the formula for f up there as well. All right. The answer to the second question for the necessary deposit to get $10,000 after 10 years can be solved as well in this context. Think of it this way. We need to solve for p. Solve for the value of p that makes the output of this function equal to 10,000. Mathematica has a built-in solving command called solve. It'll solve relatively simple algebraic equations. It doesn't work for more complicated kind of equations where you have to use what are called numerical techniques. We want to set this equal to 10,000 and solve for p. This is the basic syntax. Notice that I needed two equal signs here. That's not a typo. When you solve equations in Mathematica, anytime you're using code that solves equations, double equal signs are necessary to use. All right, so this should be the same answer we got down here, 45.28 and 90 cents. And it is. Here's the way it spits back the output, p arrow 45.28 and 90 cents. All right. What else did we do in the last video? We took this equation and we solved it for p as a function of a, just dividing both sides by 1 plus r over n to the nt power to isolate the p on one side by itself. And we got this equation, which you can write in two ways, either as a fraction or with a 1 plus r over n to a negative nt power. Either way is okay. That's what the negative exponent means. All right, should we give this a function a name? Sure. We could call it g of a, and it is a function of a. All right, a would be the only variable here, and we are switching around the roles of a and p when we do this. Now a has become the independent variable and p has become the dependent variable. G is fine here, but if I want to stress that this has a relationship to f, it is standard to use what's called inverse notation, like this. This does not mean f to the negative 1 power. That's the first thing to realize. F is not a number. It's just a name of a function. Okay, you can't raise just the f to the negative 1 power. You could raise f of a, the output of the function, to the negative 1 power, which would be, again, taking the reciprocal of the number. But f itself is just a function. You can't, it's a name. You can't raise a name to a negative 1 power. All right, so this is just notation to specify that this function is related to the original function f. Okay, it's got a nice relationship. And so we write it like this, and we call it f inverse of a. Here's another word of warning. You may have had a teacher, or maybe you have a teacher right now, who tells you, okay, now switch the variables around. Switch the a and the p around, or if there were a y and an x around, switch those around. Okay? First thing I want to tell you is that's not necessary to do. Second thing I want to tell you is, in this case, with this example and similar examples where the variables have a real-life meaning, it's a bad idea. Do not swap the variables. I do not swap the a and the p around. Not that it wouldn't define the same function if I did. It would still define the same function. However, the meaning of the variables would get switched. It would be confusing because of that. So you do not want to swap the variables. All right, let's graph these to finish off this particular video. So I'm going to graph these using some commands I've shown you in the past with Mathematica. I am also going to define the function g here. Excuse me, f inverse. I think I'll type it like this, f inv, like that, of a is going to be, all right, we can do it either way, a times, I'll use the negative exponent, 1 plus r over n to the negative nt times t power. Again, put the times in there. By the way, f inverse of 10,000 is another way to find, and we did that in the last video, this answer 4528.9. There we go, 4528.9. Let's graph these. In the next video, I will show you some important symbolic relationships between these things, and we'll go on to other kinds of functions as well. but we'll end this video by graphing them, using some Mathematica commands I've shown you before, like plot. I'm also going to use grid. I'm not going to make an animation, so I'm not going to use manipulate. Let's plot both these functions in a grid. I'm going to make one plot in one spot and another plot in another spot. Grid is a command that makes matrices, grids, or arrays of things. I'm essentially making a 1x2 matrix here when I use this syntax, where the entry in the left side of the matrix is going to be one plot, and the entry in the other side of the matrix on the right side is going to be another plot. I'm going to plot f on one side. Let's let p go from, it doesn't matter much what I pick here. I guess initially I was thinking about well, let's go up to, say, a $10,000 deposit there. So this is the basic syntax for plotting f of p. I'm also going to plot f inverse of a. I'll let that go up to 10,000 as well. All right, we'll get a basic plot here. It might be kind of big. Well, actually, the grid will make up smaller, actually. Yeah, they're smaller there. It would be good to add some things to this picture. For example, labeling the axes would be good here to keep track of what's what. I would want to label this graph on the left, the graph of f of p. A is a function of p, with p on the horizontal axis and a on the vertical axis, so I do it like this. And the other graph, I'd want to label switching those around, putting an a first and then a p. There, I've got those labels. I can make them bigger. I like doing that. I can make the graphs bigger as well. I won't bother with that for the moment. Okay? And you might ask, how are these graphs related to each other? You may have had a teacher, or you may have learned that when you do the swapping of the variables, the graphs are reflections of each other across the horizontal line, or the diagonal line y equals x in the generic case. Is that the case here or not? I'll let you think about that, and we'll think about it together in the next video.